Hi, welcome to the final part of my presentation on inverse mean curvature flow. Right now, I'm going to be talking about an application to minimal surfaces. It's a neat little application, minimal surfaces in R3. That's more or less a corollary of some work that Meeks and Yao did on minimal surfaces in the 80s. So in 1982, Meeks and Yao studied Plateau's problem for a compact three-manifold with mean convex boundary. They considered curves that lie on the boundary of this three-manifold, and were able to show that an area minimizer in M3 exists for such a curve. And they also proved a finiteness property for the minimal disks in M3 that are bounded by this curve. So this is their statement more formally. If you consider a bounded domain in R, so their theorem applies in much more general circumstances than just domains in R3, but I'm kind of modifying it just for a mean convex domain in R3. Let's say that you have a mean convex domain in R3, and you consider a Jordan curve that lies on the boundary of that domain. What Meeks and Yao were able to show is that there will be a disk bounded by gamma, which minimizes area among all disks that lie in M and are also bounded by gamma. And this minimal disk will be embedded. Also, if the curve is C4 alpha, so if you have a little bit more regularity on the curve, then you have almost finitely many minimal surfaces bounded by gamma. And what I mean by that is that there will only be finitely many minimal disks with areas smaller than K for any choice of K. So you have these nice characterizations of minimizers of for area of gamma. There will only be finitely many for any given area bound, and the global minimizer is always embedded. Now, these results only apply to surfaces bounded by gamma, which are contained within M. So if you picture a mean convex surface in R3, and you picture some Jordan curve on that mean convex surface, in general, the minimal disk of that Jordan curve can stick out of the mean convex surface. So all of these Meeks-Yao results would not apply in that case, right? Like these results don't say anything about minimal disks D, which are not contained within M, but are still in R3. So what does inverse mean curvature flow have to do with all this? Well, it turns out that if you take a surface N0 and Rn plus 1, and it admits a global embedded solution to inverse mean curvature flow, that actually gives you a nice foliation of the exterior region to N0 by mean convex hypersurfaces. So it's actually a pretty straightforward argument. Let each flow surface be the boundary of some bounded domain in Rn plus 1. These domains will nest with one another in time, and their boundaries union to the entire exterior region. So what happens if you put properties 1 and 2 together? Well, if you have any immersed minimal surface, which is bounded on N0, and you take T0 to be the imp of all times such that D is contained within the domain E sub T, you know that D must intersect the boundary of ET0. Since D is also contained within the closure of ET0, the mean curvature of D at that point is controlled from below by the mean curvature of the boundary of ET0. Well, the boundary of ET0 is just the boundary is just equal to NT0, so you have a bound on D away from 0. What does this all mean? It means that, well, D cannot stick out of N0 if N0 admits a global embedded solution to inverse mean curvature flow. If it did stick out, you could always find a point on D where it was mean convex. So all stable minimal disks bounded on N naught are enclosed by N naught if N naught gives rise to an embedded global solution of inverse mean curvature flow. I've illustrated the picture here. D is the minimal disk. N naught is the boundary of E naught. And if the minimal disk stuck out of N naught, you would derive a contradiction because the exterior region would be foliated by mean convex hypersurfaces. So, you know, there's not much more to be said. It's a pretty standard comparison principle. I thought it was cool that there was a nice little minimal surface application, and it's just a nice little corollary of the Mixed-Gauss result, but I thought I should mention it because we like applications. Okay, well, that's all I have to say this part. Thank you very much for watching my talk, and this talk has gone extinct.